really math dense, so if you're curious, I'll answer your questions, but I'll try to go in a higher level, so you guys at least are able to understand what's behind the scenes, okay? And how to adapt to new ML models, because some concepts that we're gonna talk today are going to apply to other ML models as well, okay? So let's talk about the linear regression. What we're trying to do, like we saw on the last assignment, we're trying to draw a line on our data, right? But how do we represent a line mathematically? And if you remember from your math class, it's y ax plus b. But here on the ML world, we're not calling a and b we're calling them W1 and W0. Why is that? We have this concept of ways, okay? That's going to be important for neural networks. But here what is important for you guys is that we have these variables that we're trying to find, and we're gonna call them W, okay? We are trying to make the machine learn, so we're trying to find these variables so they learn how to draw a line in this chart, okay? That's what we try to do with linear regression. And how do we do it, right? First, how do they work for the linear regression problem? The W1 is the angle of the line, okay? And the W0 is where that line cuts the y-axis, okay? So you can see W0 here, and W1 represented by delta W by delta X, okay? So with the angle and the position relatively to y, we are able to draw a line here, right? And the starting angle, we are going to get there, but that's a good question. And a spoiler, we can start anywhere. We can start anywhere. The machine doesn't know, right? So you can consider any W, 1 and 0, and that's fine. It's her job to figure it out. Okay? So how does it figure out? Like, we need to find a hypothesis W that best fits the data points. So like we just thought, we don't know which angle and which position that line should be. So we are trying to find that combination that fits this data with the minimal error possible, okay? In order to do that, we need to know what is error and what is not error, right? So they came up with this equation here, and this is what we call the loss function, okay? And what this equation is doing is trying to define the amount of errors that our prediction, our line, is having according to the data points for the reality, okay? So that's what this function is doing, and the job of our algorithm is to minimize the loss function, because we want to have the minimum errors possible. If you get the minimal errors possible, we're gonna be able to draw a line here that fits better this data, okay? So this is what the loss function is, and the way you calculate that here, you just sum all the differences between the actual value, the value from the real life, and the predicted value, the value from our function itself, that have a W and a W1 that we don't know, so we're trying to find a better one every time, okay? So those differences, we call the residuals, right? Those are these red lines here, as you can see here. All those red lines, they are like errors. These points, they don't fit this line, so we don't like them. We want to minimize them. And that's how we try to find the HW, the hypothesis W, that minimize the loss function. Minimize those red lines. We want them to be the minimum as possible, okay? So as you may imagine, there are many possibilities. You can draw a red line here, you can draw a blue line there, a green line here, and so on and so on. So in order to find the best the best hypothesis possible, we need to have certain properties on the loss function, okay? And one of the properties for this problem in particular is if we draw the loss function, this is a convex shape, right? And we assume that this loss function has a minimum value that actually makes sense for us, okay? So the W1 here, the W2 there, in 3D we see that there is something there that's the minimum value in the shape, right? And we are trying to reach these points. That's our goal. The way to achieve that in linear regressions, they have certain math techniques. I don't want to go deep on that because I don't want to talk about derivatives and stuff. But they kind of find the W1 and W0s using this formula here. And that ramsack that we used last class, and at the end of the day, it's kind of doing this, trying to find the W1 and W0 based on these math functions here, okay? An example in real life that you might want to use this kind of approach. Intuitively, we know that when we buy houses, the bigger the house, higher is the price. So there is a correlation there. So linear models, they are really good for finding correlations and predicting values according to those correlations. So in this case here, the line that best fits, we can see here the house size. This question. You can see the house size in the square feet. The higher it is, the higher the price. So we can draw a line here that kind of fits this problem. Okay, so we try to find this line. So in this case, we found the W1 and 2, and we want to see, we want to calculate that, like the efficiency of that. So there are certain techniques for finding the efficiency. One could be the least square sum of the differences, which is pretty much this formula here. We try to minimize the sum of the difference, the square sum of the difference. This is what this is talking about. But there are others, like these R2 here. Okay? And that's kind of another way of representing that formula, okay? So let's see that from another angle. Let's say, like the example that we talked before, right? We don't know where to start. So a good way to start, let's say, the mean line, which is the average of all data points. So we can draw a line here, and then we can tweak that up or down according to observer data. So let's say we found this data here, we have something, and then we find the difference here of them. That's another way of trying to tweak that line. And that's what this formula is doing here with the sum of squares, total sum of squares. So we do the actual value minus the average, and we make the square. and then we try to find the y, the W0 and the W1 based on those values. Okay. And the coefficient of determination, like the other formula that I was talking about, there are two, is basically the division between the SSR and the SST. The y predicted, the sum of the difference between the average and the y predicted, and the sum of this SST. That's sum of square. Sum of squares. Yeah. Let me see if I can find this here. Sum of total squares, the SST. Okay? Yeah, so as you can see, there are a lot of formulas related to this. What is important for you to know is here we have this concept of loss function, okay? There is always, when you try to minimize a loss function, we are trying to reduce the amount of errors that your ML model has, okay? And that loss function can change according to the problem that you have, okay? So that's one thing to consider. Another thing is these W's, they are the numbers that we are trying to find. I'll talk a little bit more about it during the neural network part, but those are the numbers that they kind of define how your model is going to predict the results, okay? And yeah, that's how you find the angle and the position of your line, because you start from, let's say in this case, we're starting from a random line, the mean, and we are trying to tweak according to the results of the R2, okay? So, in order to do that, we come with that the test of hypothesis. So, let's say we start from somewhere, we don't know if that's a good one, a good result, and then we try random values. And then we test that alternate hypothesis, which is based on the random values. If that minimizes our loss function, that means that the new hypothesis is better than the previous one. So we substitute. And continue doing that until you're satisfied. The neural networks, they work pretty much like that, but they use different functions. But the idea is the same. You keep iterating across the data and try to improve based on the data that you learn with new hypotheses, okay? So that's all that math is just for one variable. I don't know if you guys remember, the data sets we had the features and the targets, right? The features are the things that define our domain. So let's say here the size of a house, but let's say we want to have as well the number of rooms or the number of bathrooms. Those are different features and those are different variables. So we can use similar math for this multivariate linear regression. The idea is the same, but here we have instead of one x, we have several x's, like n x's, okay? That can go to the infinity if you want. And as you can see here, we have different w's as well. That kind of defines this formula here, okay? So yeah, that's the basics for linear regression. Do you guys have any questions regarding this? And if you guys didn't understand, feel free to say, I didn't understand, I can explain again. just want to make sure that you guys understand these concepts. The ways we are trying to find a function that is the best for that problem. The way we define is by minimizing the loss function, because we want that to be the most accurate possible. And we can measure the efficiency with certain formulas as well. In this example, there are two is a good one. There are others out there.
Do we need to memorize these formulas, or?
So the catch is when you use TensorFlow, those formulas, they are kind of built in on the system for you. So you might need to memorize, especially the names, because certain situations, certain functions are better. In practice, that's a lot of trial and error, but you need to know the concept, like the concept of you have a loss function, you want to minimize the loss. You have certain numbers that define your ML model. Those are the ways. Those things I really recommend memorize. These details, like how the SSR is calculated, SST, I don't think so, but you need to understand how they came up with this idea. So here, they are trying to just calculate the difference, sum everything, and get a number. That's pretty much it. Okay? And also, of course, how to apply in real life. So if you have any problem that you know that a variable, the higher the variable, higher the outcome, let's say the size of house prices, you know that this model might fit your case. All models, they have their own characteristics. We are not going to the details of all the models that are out there. If you want to ask questions, I can answer. Like a guy earlier talked about the genetic algorithms, I can show some explanations. But what is important are the concepts. Ways, function laws. We are trying to find a function that best fits our problem. Those are the concepts, like the main concepts I said. And the idea of iteration across hypotheses as well, like this idea here. You don't know something, you try. You don't like it, you try something else. And if that's better, that's your new hypothesis. Okay?
Like, how do we know, like, for that problem, we have to use that formula, or?
Yeah, so that's somewhat experience, somewhat understanding the formula. Because let's say SVM, it's another machine learning model. This one is really good for separating data. Like you draw a line and you separate data. So you classify, let's say, dog, not dog, for example, in images. You can do this way. There are other techniques like k-means. I think it's k-means. Yes. That instead of drawing one line, you draw several lines starting from one point. So you kind of have to know this stuff. And in order to know, usually if you go to the, let's say, k-means, scikit-learn. Sometimes they show on the user guide, but sometimes they have like the research paper as well. So you can go there and study that. So you know, you kind of know if that fits your problem or not. That's how usually you do in real life, okay? In my case, I had the lucky of have researchers on my side, so they were kind of doing that job, and I was kind of applying based on the math that they found. Okay, so that's why I don't want you guys to go crazy with the math, but I want you guys to understand the concepts behind the math. Like, we are trying to reduce the amount of errors. That's what the loss function is. We are trying to find numbers that are going to fit our problem. Those W, they are that. Okay? And so on and so on. Is it clear or?
Yeah.
You can say no. It's a lot of math, I understand.
Yeah, it indeed looked really hard.
Yeah. You can go hard. You can go as hard as you want. Yes.
Okay. Can you go down a little bit?
Yes.
On the red graph, that one. Can you cut your data? Like right now the red circles are the data, right?
Yes.
And the blue line is supposed to be like what you want to calculate.
Yeah, it's your prediction in this case.
Yeah. Okay. So can you cut your data like now you have so many reds from both sides. Can you cut a certain amount of data from each side, make your data smaller so that it's more processable?
Yes, that's actually one of the techniques that people do. The way you cut it is another problem by itself. Usually if you search something by how to remove outliers, like the last class we talked about outliers, that's the data that you usually want to remove, because not only they pull in previous class, it was pulling the line down, but also it could, sometimes you have a lot of data and you don't want to process, like you said. Another technique that people use, and that's not just a technique, it's also good practice. You need to split your data between training and test. We're gonna do that today on the assignment. But the idea of that is not only have less data to work with, so you can make your stuff faster, but also you can test with the data that the model doesn't know. And that's important because sometimes that actually ties to the next topic. I'll hold that thought because I'll explain deeper on the next topic. But yeah, it is important that like sometimes you want to reduce the amount of data so you don't take like days or hours training your model. Yeah.
Thanks.
Any more questions? Okay, if not, there is an activity for demonstrating. This is not part of the assignment, and also based on the previous class, we took a lot of time on this math part, so if we have time, we're gonna do it at the end, or not, because I know now it's late, so if you guys want to leave earlier, I don't understand. But what I want you guys to take from this is these charts here. Like, you see this one? Those lines, you can imagine those as functions, right? Those are the functions that we're trying to find. So in this example, this function is fitting perfectly every point. Okay? This is actually not good. Why? If we create another point, this line won't guess it right. So let's say this point here. It's really close to a line, right? But this one is saying that's far, right? Because there is this curve here. Or even this one is even better. Like, look how far it is from the actual value. But now, let's try the same thing here. Look how close it is from the line, right? This chart here is basically what the overfitting is like. This term called overfitting is when you train your ML model so well based on that data that kind of memorizes the response. Imagine you're studying for something and you know all the answers for that test. But as soon as someone else comes with a different question related to the same topic, you don't know. That happens with ML models as well. That's basically what overfitting is. So here, would guess really bad, the response. But here, because it's not overfitting, would guess better. But also there is the term underfitting as well. It's when you go super far away from the response. So let's say the mean line here. This is under fitting. It just doesn't care about the data, right? So this is super far from everything. And not necessarily needs to be aligned. It could be some crazy shapes as well, like this one. So this one is fitting better than this one. So for this problem, wouldn't be that bad, but this one would be insanely bad, right? Because this is overfitting a lot. So if in the real world, by any chance, you create a ML model that's great, like 98% accuracy, and you get a data from the real world, and you start to guess stuff wrong, most likely the ML model that you're using is overfitting the training data. So you need to tweak something there to avoid this scenario here. Okay? So this concept is really important. And you might see that on neural networks as well, so that's why I'm explaining that here. Any questions regarding this? Okay. So let's move on. All right, so this is the drawing I think I did on the first class. In traditional programming, right? We have the data and we have the code. Once we have the data and the code, we tell that to the computer and we get an output, right? For machine learning, we have data and we have the output. We put on the computer and then we get the program, right? The way the computer finds the program is by running those math models, optimizations, and things that we talked before, okay? Reducing the loss functions, things like that. So, the neural network, what are they? They are like a math representation of the brain cells, okay? So you're gonna have a little bit of biology here, right? So how do those cells work? They have the cell body here that has the nucleus and whatever stuff they have inside. They have these axons, the dendrites, and the synapse itself. Okay? So that's how the real neural cells work like, and these look like. And they have certain properties, okay? So the neurons, they collect signals from inputs, the dendrites. So this part of the cells here, they get inputs from other cells, from other neurons, okay? Sends out spike electric activity on the axon, 2,000 branches. So the axon here, you see the axon here, it sends electricity through the synapses to the other neurons, okay? At the end of each branch, a synapse converts an activity in an exciting or inhibiting activity of a dendrite or another neuron. So this interaction here on the synapse is telling the next neuron cell to activate or not. Okay? The neural fires is basically the idea of the synapse again. So this another way of seeing this sentence here is this function, let's call it function now. Whatever is inside only activates if certain conditions on the dendrites activates as well. Okay? And learning changes the effectiveness of synapses. What does that mean? When you are a baby, your brain is not, it's new, right? There's nothing learned there. So that means that every neuron is kind of connected to every neuron. Everybody there is connected. um, not every, but the adjacent ones. Let's say these ones here. The synapses, they are all working, right? Over time, as you are learning, those synapses, they start to weaken. And that's how our brain actually stores data and stores concepts, and we actually learn. By having certain cells activating and deactivating in certain situations. Okay? So that's what this synthesis is. So that's how our biological neuron works. And we got this idea and we transformed in this math representation of a neuron, the perceptron. Okay? So this is what the perceptron looks like. It's like a step function here, and it has not necessarily has this is the step function perceptron. Okay, so this is one of the functions that could be on, let's say, the nucleus of the neuron. So this one only has zeros and ones. It's not continuous. This representation you can see here, like there is a gap between these two. And there are some problems with that, like it makes really hard to minimize the loss function in a smoother way. So that's why people tend to use more continuous functions, okay? Maybe before going to other functions, I'll try to explain this in another way. Remember the function from the linear regression here? This guy, maybe this one is better because there are more neurons, like this. Imagine that function is being the function that's inside the cell of your neuron, okay? The inputs, the dendrites, they are your X here, this XJ here, okay? And the synapse is basically what we are going to study, these perceptrons and the functions that are going to activate or deactivate a neuron, okay? So that's another way of seeing what we are going to study. And I'll show some of those functions now for you guys. So we have the sigmoid. This is how it looks like. It's a function from 0 to 1 that has this like smooth shape. Okay. This is the math formula if you're interested. We have other ones like the hyperbolic tangent. As you can see, it's another smooth transition between zeros and ones. You don't just turn on and turn off a neuron. You have like a smooth transition. And there is another one that's super popular, the ReLU function, which is like if it's negative, the value, you just ignore that. So you make like a linear function that's that doesn't accept negative values, okay? There are variations of that. There is the soft plus function. It kind of has the same shape, but it's a little bit smoother here, okay? There are other types of functions as well, and all of those, they have like different shapes. As you can see, you can go hard limit like the beginning, you can go symmetrical. Every time that you see symmetrical, it means that you accept negative values as well, like deactivate or activate the next neuron. You can have linear, you can have this saturating linear, which is like, you see there is a line here, a horizontal line. You can define that and make it like a smoother transition or a harder transition. You can tweak that You have the log sigmoid, which is similar to what we saw before. We have the hyperbolic, the normal one that you know, and you have this one that's a technique that's pretty much saying connect all the neurons, right? That's why we call it competitive. Okay? Now that we know those are all those functions, they are just the synapse part, okay? And they work better for different situations. In the TensorFlow framework, that will be pretty much just a string that you configure. We're gonna see on the assignment today. But what is important to know is this concept, okay? Now, we're gonna talk about the neural networks, okay? How does a single neuron look like? We have a P as the input that we multiply by the W here, and we sum with some sort of constant that might be there already on your neuron, and then that provides the result of a function that we send forward to the next neuron. Okay? As you can see, this really looks like the linear function that we were studying before, like the normal function, right? Yeah, and that's how it works. This F here is the synapse that we were talking before, okay? So let's say you reach certain value that our synapse just deactivate. That's how it's done, like that's how you deactivate the next neuron, okay? Because you're not sending data for that. So here are a few examples if you want to run those. So the W3, B2, the inputs. So you get certain values, and then you send that to the function that defines our synapse. Okay? So that's how a single neuron works. But of course, that alone doesn't do much. So we had this idea of having layers of neurons. Okay? And what do they look like? They are several neurons that might be connected to the input. In this case, they are. And then they provide certain outputs. So imagine, remember those NumPy arrays? Imagine we are sending them to certain function, and that function is providing another NumPy arrays. It's pretty much what these look like. Okay, so this is the input P. We connect them to the weights associated to the neurons, do the math behind, and check the synapse if we want to move that data forward or not. Okay. There are other representations of neurons as well. You can see there is this one that's just like a simplified version of this, or you have this one. The math here, if you want to read this, you see this W here is a capital W that represents that's an array, okay, or a vector in math terms. In coding terms, that's like one of the NumPy arrays or pandas that we were working before, like the series or whatever. Okay? Now, things start to get fancy. After they came with this idea of a single layer of neurons, that's what people call neural network, right? They came later with the idea, why not have several layers of neurons, right? That's kind of the deep neural network. It's because they are deep, they have several layers. So in this example here, we have the first layer similar as before, but now that layer provides an output that's actually the input for another layer. And now those neurons, they are connected together in this flow here. And the result for the A3 is going to be the the result of functions, as you can see here, the result of function 1, the result of function 2, the result of function 3, because they are connected together, they are in cascade.
I'm sorry, so the output of F1, it's gonna be the input of F2?
Yes, that's how it works. There are other ways to represent that as well. So here we are representing with matrices. So we have this W, big capital W here, which represents the array of ways. So now we are coming back to this again. Remember we are calling ways before, the A and B. The neural networks, they do the same here. Those are the ways for your neural network, in this case, because they are layers, right? So that's how the math representation and also the math inside those neural network works. And how do we find the initial problem, right? The hypothesis, the best hypothesis. We are trying to minimize the loss function. How do we do that? We do these optimization methods, okay? So we try to find the W's and B's that makes more sense to our problem. And then we feed the neural network with that data using techniques like the gradient descent, yeah. So that's how it works. Like you provide data, you see the results, how far the results are from the reality, and then you figure out with the gradient descendant where to tweak in the neurons so you get better results. Okay? Any questions regarding this? Because this is a lot of things. I really need you guys to understand these concepts because the code is simple, but understanding the code is a little bit complex. So I really want you guys ask questions now, because yeah, if you don't ask them, maybe you are not going to be able to understand the code, and I don't want that.
I think like during the code, if you remember, it's like this is what it said about da-da-da. It's
Yeah.
better because I mean I get this stuff, but Brett's good.
Okay, yeah, for sure I'll come back to this. And I'll see if I provide some YouTube examples as well, because I saw a video earlier today, people were asking about genetics algorithms. And there is a video about a guy that made an algorithm that managed to finish the Super Mario Bros. Game using a code, and the idea that he used was similar to this. So these inputs and outputs, they can be anything, including the AI of a game, for example, right? Alright, so if you guys don't have questions, we can start with the carrots then. Alright.
Yeah.
Yes?
Yeah, I have a question for.
Okay.
So, like, could you take an example, a system catching these instructions, like, like just catching these instructions for doing something. You know what I'm saying? Just a neural system. I mean. So, is there any real systems that you know to take an example?
Google is an easy one, right?
Google. So, in which point?
So probably they don't do like this anymore, but I've seen models that were like that. Imagine the input here, they are the letters that's like the first NLP. It kind of worked like that. Imagine you have 26 neurons here, and each one of those neurons, they represent one of the letters of the alphabet. Okay?
Yeah.
So what they try to do is they train this neural network, and then they try to predict what you're going to type next. Another good example for that is the keyboard on the iPhone or Android. they predict what you're going to type,
Oh,
right?
yeah.
So that's how they do it. Like they have certain neurons here that represent the input, whatever you have. Now I think they call context, but just imagine
Oh,
that
this is
as
just a
input.
part of the machine learning, right? Because like the inputs, you know, for the keyboards and iPhone, so that's.
Yeah, a lot of stuff we use machine learning to do.
Okay.
Usually the hard part about this is to figure out what kind of neural architecture fits better your prompt. So that's why you need to know well how your loss function works. That's why I was trying to explain this one hard, like here. You need to know that your loss function makes sense, like it has a minimum value, for example.
Yeah.
Other stuff are based on research. So nowadays they talk a lot about convolution neural networks, which are neural network architectures good for images. So a problem we had in my previous job, we are trying to identify the letters of a plate in a random image. So that's a problem that comes from this, like the pixels. We're gonna have that on the example today, the assignment. But yeah, the pixels, they are represented here as well. I think that's why they put P here, I don't know. Yeah, that's the input. Yeah, anything like, I'll even show this.
What about just biometric systems? Biometric systems are catching the following, those instructions for a neural system.
Which is
The biometric system, so can recognize your face and to kind of that, you know, like for example.
Yeah,
so
they could use a standard
finger
image.
touch.
Yeah, they could. Probably they have better techniques for those stuff. Because this one is, as you can see, super generic. It works for everything. We could use that for that kind of situation. But let's say, you know how a linear function is. Do you prefer to use like high school or elementary school math techniques to find that? Or do you prefer to train a neural network for that? Like, there is this balance. Certain models, they work better because they are not only faster, but they solve known problems. Neural networks are really good for problems that we really don't know. Doesn't mean we need to use that for everything. Because it's like a brain, it acts like a brain, really. Like it learns and adapts.
Okay.
But we don't know how big the brain should be or how the neurons should be connected in order to adapt and works in an efficient way for a particular problem. So there is a lot of try and error. Okay. Okay, so if we don't have any more questions, I guess we can move on. The only thing that I'd like to show, because I showed that on the last class and I really like how that went, is
Grayscale.
no, genetic. I want to see if they show, yeah. Like, I want to see, they had a drawing here. Yeah, right? So here they talk about the generation. Like you see the chart, like we are trying to minimize the loss function. In this case, we're trying to maximize the winning function because we want to cross the stage, right? So this is an example of a kind of chart that we might want to draw. And if you see here, like every one of those buttons we could represent those as neurons from the output of our machine learning. And the input could be the image itself. Don't know if they have it here. Like the one that I saw was really good because it was showing the image of what actually the machine learning was seeing. Here's not showing, but it's fine. It shows, at least it shows like, here's the like the math representation that's happening up behind. You can see those like as neurons being activated based on the input and output. So this could be, this image here, this square, could be the input of your ML model. Something crazy happens in the end, and we have a last layer here, that's the output. Okay? So this is really similar. That one he didn't draw, but that's really similar to this drawing here. The first layer where you manage the input, the last layer that manages the output, and you have something crazy going on in the middle. Okay? So that's how you could map and create ML models for like any kind of problem. Okay? And you're gonna do one of those today on the assignment. Any questions or curiosity or whatever? Okay, if not, let's go to the assignment then. Yeah, we're gonna have TensorFlow today. Now that you guys know Jupyter, honestly, I'm okay if you guys run on the collab only. The assignment says to run locally and on the collab. Honestly, the collab for me is enough. So I'll do that now. I'll create a new Jupyter notebook. And the reason why I'm doing that is I don't want to have weird version issues like we had a few classes ago. Even here in the comments, they say, oh, you can specify a specific version. Honestly, I don't want to hit you with those problems. On the collab, we don't need to install anything. So you're gonna have a happier life there. If you're brave, feel free to run locally. It should work. I'm just not brave.
What do you do for your projects?
What?
Do you use what ID?
Okay, so for the project, I need to see the requirements again. But if you need to run a POC with your ML model, you can run a Jupyter Notebook anywhere. And then you can copy and paste the code that you generated there, or even the ML model itself. Today you're gonna learn how to save it. For saving, I'm recommending to run locally, but you know, it's the same idea of the loading that we have with pandas. And once you have the ML model, you can load that anywhere. So you can load that, let's say you like Java. You can use the Android Studio and load that from the Java world, okay? Or if you really want to do it in Python, you can do PyCharm, it doesn't matter, okay? So yeah, let's run the examples of the activity 1. Okay.
It's on V5.
Module 5, TensorFlow and Keras.
She's
Is it only-
behind.
What?
She's really behind.
No, it was just fun.
No, that's fine. If you understood the math, I'm happy. That's the hardest part of today, honestly. Because you see, if I actually want to make your life harder, I would want you guys to do this stuff. I really don't want to. I really don't want to make your life hard. And the code today is easy, but understanding this code is not easy at all. So that's why I went through the math part with you guys. Okay? So in order to reach this assignment, you just go to the module 5 and go for this TensorFlow and Keras, okay? Okay, let's go then. So we're gonna run the commands. Here on the assignment, they kind of recommend to run on the idle. You see these arrows here. I don't really want to do that. I honestly prefer the Jupyter notebooks, not that to have access, so let's do it by there. And in order for the assignment itself, you can generate a PDF here if you want, or you can keep the print screens that we were doing before. I'll do this activity here.
Is it only, Professor? Is
Huh?
it only, we are working for activity 1 and activity 2?
1, 2, and the examples that are annexed. They don't say activity 3 there, but there is kind of the activity 3. If you want to see the requirements, it's written here. Complete activity 1 and 2, and for the activity above, like there is another activity here, the examples. Run them in collab and rerun in local. Honestly, I don't care if you don't want to run locally, but I want to see you guys trying out those commands, okay?
Okay.
However, if you run it locally and you manage to save, I think I'll give some extra points for that. Okay? Alright, so let's go to the commands. Activity 1.
If we run this on local, you give extra points.
If you manage to run locally and you manage to save the model. Because there is a portion here that save the model. I don't know if you're gonna have enough time to show this today because I'm running a collab. So I'll give you extra points if you manage to save and load the model. We're gonna run this command on collab, but it's going to fail because that's not the local machine. So that's why I'm giving a heads up.
On the local machine, we cannot even install the TensorFlow and Keras. Just for the like version number, and when I did the version number, it still says it's a version number.
Really? Let me try to run that command then. No, I just see this error. Yeah, in my machine is working.
Mine asks for a version number, but when I do the version number, it still says it.
Which one are we going through? The first one, just pick response and support, or the second one?
Attack both.
Both? No, if you do just first one is enough. It's very
Yeah, I tried the first one, it didn't work. I tried the second one.
No, you don't have to try. If you want this one specific version, you can, but you don't need it.
But I tried the first one, it didn't work.
Oh. It's low for you.
Let me see what's going on. That's why I prefer collab. If you really want to try, you want to put that. You know, try. But can you try that again? Do you have just PEEP installed or no? No, but I mean without the tree. Try PEEP version. Okay, okay, honestly, I think we're gonna need to search about that. Maybe if you go to the official website, you're gonna see the version there, and then you can try one of those versions. We are not going to do anything fancy today, so whatever version should be fine. A good version for you. Yeah, try this one. See if it works. Yeah, mine works. It's already installed actually. honestly, I don't know.
Let's
I'll-
use Jupyter.
It's probably a local environment issue. Like here, I installed normally, right? So what I would do to track this problem down, if you really want to do, I honestly want to move with the class because of the time. But I would try to check the version, check if the version is the same. If it is the same and it's still creating issues, I would try to search online to see if there is any other people have issues, because it might be a Mac specific version issue. And I'm saying that because I use Mac as well at work, and from time to time I have this kind of weird errors that nobody's having.